Hello, my name is Awang Muhammad Amir Shukri bin Awang Marzuki. In this video, we will talk about image encryption using chaotic maps and DNA addition operation and noise effects on it. Written by Manisha Raj and Shelley Garg and published in International Association of Scientific Innovation and Research, 2019 on 24th January on pages 1 to 6. In this video, we will discussing about the paper that talk about methods to encrypt images, and we will covering about the introduction, objective of the paper, explanation and demonstration of the purpose technique, example, results and conclusion of the paper.
In the era of widespread digital image transmission over the internet, security vulnerabilities pose significant challenges. The imperative for real-world security extend to critical applications like medical image system and military information system. Chaotic system characterized by deterministic non-linearity in features such as periodicity and sensitivity to initial conditions present a novel avenue for cryptographic solutions. Chaotic-based image encryption seems leverage position, permutation, and grayscale substitution, which derive robust defense against latent attacks and assurance with encryption. Concurrently, the burgeoning fields of biomolecular computing at the intersection of molecular biology, chemistry, computer science, and mathematics is experiencing rapid growth.
This research paper was made based on 5 objectives, which is to propose a new digital images encryption based on the linear chaotic map to meet the requirement of secure encryption. Next is to conduct a security analysis, including key space analysis, sensitivity analysis, and differential attack analysis to evaluate the purpose of encryption scheme. The third one is to explore the ability of the encryption algorithm to resist exhaustive, statistical, and also differential attack through key sensitivity analysis, correlation coefficient analysis, and also histogram analysis. The third one is to compare the effectiveness of different chaotic maps, which is Daphne map, Tinkerbell map, and also gingerbread man's map in encryption images to determine the best encryption effect. The last one is to investigate the effect of noise on the encryption images and suggest a future research direction for noise filtering and also deblurring algorithm.
Next, I'm going to demonstrate about the image encryptions using the following techniques, which are chaotic maps, DNA addition operations, and noise effects. In this paper, there are 3 chaotic maps, which are Duffing map, Tinkerbell map, and gingerbread man map. First of all is the Duffing map, which is also called Holmes map, which is a discrete time dynamical systems. This kind of Duffing maps, it exhibits chaotic behavior. It takes a point which is x of n, y of n in the plane and maps it to a new point given by the formula given, which is x of n plus 1 is equals to y of n, and y of n plus 1 is equals to minus bx of n plus ay of n minus y cubed of n, and with the 2 constants, which is a and b, and and they usually set a is equals to 2.75 and b is equals to 0.2 to produce the chaotic behavior. Secondly is the Tinkerbell map, which is also a discrete time dynamical systems given by x of n plus 1 equals to x squared of n minus y squared of n plus a multiplied with x of n plus b multiplied with y of n, and y of n plus 1 is equals to 2 x of n y of n plus c multiplied with x of n plus d multiplied with y of n. So from here we can see that there are 2 groups of the constant values, which is a, b, c, d. So from the first group, which is the commonly used, is a is equals to 0.9, b is equals to minus 0.6013, c is equals to 2, and d is equals to 0.5. And the group 2 is a is equals to 0.3, b is equals to 0.6, c is equals to 2, which is remains same, and d is equals to 0.27. So like all the chaotic maps, this Tinkerbell map also have some periods, and after a certain number of iterations, any given point shown in the map will find itself once again as its starting point, which you can see the diagram on the left side. Last, we have gingerbread man map, which is a chaotic 2D map in this dynamical system theory, and it is given by the transformations with x of n plus 1 equals to 1 minus y of n plus modulus x of n, and y of n plus 1 is equals to x of n. So you can see the diagram on the left side. After we done understanding the basic theory behind the chaotic maps, now we proceed to the scheme for encryptions and decryptions of image. So in this part, we are going to learn about DNA encoding and decoding, and also the additions and subtractions algebraic operations for DNA sequence. So in DNA encoding and decoding, the information of this DNA is made up of 4 nucleic acid bases, which is adenine, guanine, cytosine, and thymine, which is denoted as A, G, C, T respectively. So these DNA bases pairs up with each other, which is A with T and C with G, which are complement to each other. So in binary mathematics, 0 and 1 are complement. So 0, 0 and 1, 1 are complement. And similarly, 0 and 1 and 0, 1, 0 are complement also. So since A and T is pair up and C and G is also pair up, so 0, 0 will be A, and then conversely in T it will be 1, 1 because they are complement. So the example will be 0, 0 equals to 1, 0, 1 equals to C, and 1, 0 equals to G, 1, 1 is equal to T in this paper. Okay, so next, how to apply this DNA sequence into this pixel image. So in the 8-bit gray images, which is 256 times 256 pixels, each pixel is given by a DNA sequence of length 4, which you can see is the AGCT. So if the first pixel value of the original image is 1, so we will convert it into the binary stream, which is 10101101 as an example. So by using this DNA encoding rule to encode the stream, we get n sequence, which is TTGA. By using the CATG, denote 00, 01, 10, 11 respectively. So to decode above DNA sequence, which is TTGA, we can get back the exactly same binary sequence, which is 10101101. Next, we have addition and subtraction algebraic operations for this DNA sequence. Actually, this addition and subtractions operations for DNA sequence, they perform according to the traditions, additions and subtractions. So, how to say that? For example, 1, 1 is T, and it plus 1, 0, which is G, we will get 0, 1, which is C, because 1 plus 0, we will get 1, and 1 plus 1, according to the binary stream, we will get 0. So this is the additions, algebraic operations. So we can refer to the addition operations table, and this addition algebraic operations table is a double helix structure which has satisfied the Watson's-Crick complement regulations. Okay, so in other hand, subtractions is the inverse operations of additions with whose structure is not a double helix structure. So from this subtraction operations, we can see that 0, 1, which is C, minus 1, 1, which is T, we will get 1, 0, which is G. Yeah, so like 1 minus 1, we will get 0, and 0 minus 1, according to the binary sequence, we will get 1. So this addition and subtraction algebraic operations, we will refer to 0, 0, which is A, and 0, 1, which is C, and 1, 0, which is G, and 1, 1, which is T in this paper. Next, after knowing the theory and the scheme for the decryption and encryptions for the image, now we proceed to the proposed encryption algorithm, which is based on the DNA sequence additions operations. So first of all, we will need to produce a secret key using original image, and then secondly, we will need to divide the original image into blocks and add blocks by using the DNA sequence additions and carry out DNA sequence complement operation. And then last, we will decode the scrambled DNA matrix to binary matrix by using the rule and then reconstruct it to an image matrix again. So with this algorithm, we will be using the 0011 and 01 and 10, which is denoted as A, T, CG respectively. So first of all, the first step is to generate the sequences by using the input of 8-bit grayscale image A as original image, which is A equals to A bracket Aij, and which is the Ij is the positions of the image as the Aij is the pixel value of image, and then M and N is the size of image. So in this 8-bit grayscale image, which has 256 different shades colors, which is 0 stands for black, 127 stands for gray, and 255 stands for white. So we will be using K1 and K2, which are the small blocks called cells, which are calculated using the following formulas. Next, for generations of two chaotic sequence, we need to choose two initial values, which is x1 and y1, and four system control parameters, which is mu1, mu2, mu3, mu4, which will be used in the algorithm later. And this x0 and y0 can be calculated using the following pseudocode, which is x0 equals to x1, which is the initial values, plus k1, which is the cells. So if x0 is larger than 1, then x0 will automatically become modulus of x0, 1, else x0 will remain same. Next, I'm going to demonstrate about the algorithm principle. So this part we will be divided into two, which is encryptions and decryptions. So first of all, from the encryptions, which is the first step is binary conversions, which is convert the original image matrix into a binary matrix. And then next we will be using the DNA encode root to obtain a matrix K of size M and N times 4. And then next we will be doing division into cells, which is divide K into small blocks called cells, which is K that I mentioned earlier before, which is Kij of size 4 times 4. And then third is chaotic sequences, which is generate the two chaotic sequences x and y using the chaotic maps with initial values x0, y0, and the control parameters. And then fourth is the matrix operations, which we will be reconstruct x and y into row and column matrix respectively. And then next we will be perform a multiply operations on x and y to obtain a matrix K prime. So we will be using this K prime to convert it to a binary matrix using a specific equations. And then next we will be doing is divide matrix K prime into small cells K prime Ij of size 4 times 4. And then fifth is the DNA additions, which we will be add the Kij and K prime Ij according to the DNA additions rules to obtain the added cells Bij. And then 6 is the recombinations, which is we will recombine the small cells, which is Bij, to get a new matrix C. And then 7 steps is the chaotic sequences again, which we will generate two chaotic sequences, which is Zi and Zi2 of length of M and N times 4. And then we will reconstruct the Z1 and Z2 into the matrices Z1, which is M1, and Z2, which is 1 and N times 4. And then we will be perform a multiply operations to obtain the Z matrix of size M, N times 4. And then the X steps will be threshold functions, which is we will be using the function which is to map the values of Z into the 0, 1 using a threshold functions, which we can see the functions shown below there. So last, we are having the complementation step, which if Zij is equal to 1, we will need to complement the corresponding element in matrix C. Otherwise, we will leave it unchanged. And then we will obtain a complemented matrix P. Okay, so this is the whole process for the encryptions. And now if we want to decrypt it, then we will need to carry out the inverse process of step 1 for matrix P first, and then we will need to obtain the real matrix D, which represents the encrypted image. So this whole decryption process, we will need to start from the inverse process until step 1, except that addition operation is replaced by the subtraction. So the receiver need to obtain the secret key from the senders is for decryptions. Okay, so last, the technique is the noise effect, and this paper they use salt and pepper noise, which is similar to sprinkling white and black dots on the image, and you can refer to the image. The left side is the original image and the right side is the image after applying the noise. So that's all from me. Now I will pass it to next person. Thank you.
Good encryption algorithm should resist all kind of known attacks such as exhaustive attack, statistical attack, and differential attack. So in this section, we will discuss the security analysis on the proposed encryption scheme. First one, A is ability of resisting exhaustive attack. So here we will be discussing about key sensitivity analysis. So chaotic maps are highly sensitive to initial condition and system control parameter, meaning to say that if there is a minute change, then decrypted image will no longer be similar to the original one. So as we can see here in the figure 2A, BC, show the decrypted image and corresponding histogram with wrong secret key. So here we can see the given correct key is 0.7199 and then the incorrect key is 0.719900 and so on until 1. So here there is only a small difference between the correct key and the incorrect key in terms of decimal places, but the result show the histogram is fairly uniform and then the decrypted image is different from the original. So it is proven that algorithms are sensitive to the secret key because a small changes in secret key change the result of the decrypted image. Next one is ability of resisting statistical attack. So in this part we'll be elaborate about histogram analysis. So histogram show the number of pixels for any gray value in the image, enabling statistical analysis of the original and encrypted image. So in the figure 3, it is show the gray of histogram of the original image and the encrypted image. So A is gray histogram of original image, and B is gray histogram of Duffing map, and C is gray histogram of Tinkerbell map, and then the last one is D, gray histogram of Gingerbread Man map. So based on this figure, after comparing all the histogram, so we find out that pixel gray value of original image are concentrated on some values, but the histogram of the encrypted image is very uniform, and that the encrypted image transmitted do not provide any suspicion to the attacker, which can strongly resist statistical attack. Gray histogram of Duffing map B show the best result. Subtopic is correlation coefficient analysis. In this part, the horizontal, vertical, and diagonal correlation coefficient of pixels is studied. So 2000 pair of addition pixels, which are horizontal, vertical, and diagonal from the original image and encrypted image, are chosen. To test the correlation between two adjacent pixels in plain image and encrypted image, we can use formula of correlation coefficient as shown, where we can see that the formulas such as mean, variance, covariance, and correlation coefficients. So in this formula, x and y are gray value of two adjacent pixels in the image. In figure 4, correlations of two vertically adjacent pixel A is original image and B is encrypted image of Duffing map, C is encrypted image of Tinkerbell map, and D is encrypted image of gingerbread man maps. So based on the figure on the correlation between adjacent pixel is greatly used after the encryption. Table 3, 4 and 5 show the detailed analysis. So based on the result of the table, the correlation coefficient of the adjacent pixels in encrypted image very small. Thus, the proposed image encryption algorithm has strong ability of resisting statistical attack. So the last one is C, ability of resisting differential attack. So differential attack happen when the attacker often make a slight change for the original image and use the proposed scheme to encrypt for the original image before and after changing. So by comparing the two encrypted image, the attacker can find out the relationship between the original image and the encrypted image. So to evaluate the influence of one pixel change on the whole encrypted image, two common measures are used. The first one is the number of pixel change rate, NPCR, and the second one is unified average changing intensity, UACI. So based on the formula, we can see of the two measures where E1 and E2 denote two encrypted images respectively, and W and H are width and height of the image, and the grayscale value of the pixels at grid ij of E1 and E2 are labeled as E1 ij and or E2 ij respectively. The results are opened by simulation for all three maps and shown in the table 6.
Hi, my name is Wayne. Now I want to present about the results. In our pursuit of cutting-edge data security, we will develop a revolutionary approach to encryption, combining the power of chaotic sequences and advanced encryption techniques. Our encrypted signal utilises a chaotic sequences meticulously mapped from a predefined initial value. This sequence is fortified by intercepting a pseudo-random sequence, resulting in a complex process involving encryption product, operations, interceptions, methodologies, and sophisticated computational models. Now, let's talk about the security level. The chaotic signal extreme sensitivity to initial conditions and long-term unpredictability makes it a formidable input to our encryption process, comparable to the security level offered by DES encryption. Notably, the DES algorithm introduced a significant non-explicit correspondence between its input and output, enhancing the overall security of our system. To further bolster security, our text-based approach effectively mitigates vulnerabilities associated with DES. It addresses weaknesses related to key exposure and guards attacks. The proposed method demonstrates resilience against contemporary threats, specifically countering linear analysis.
This study explored a novel approach to image encryption that makes use of codec maps and DNA sequence addition complementary abilities. Important lessons learned include synergy and enhancement. DNA addition and complement operation effectively scramble pixel value, creating a robust layer of encryption. This is further strengthened by the unpredictability and sensitivity of codec maps, particularly the Duffing map, which emerged as the superior choice due to its large key space and enhanced encryption performance. Security fortification. The combination of DNA and codec maps create a multi-layer defense against various attack types, including burst wars, statistical, and differential attack. This heightens security strength from the immense secret key space and extreme sensitivity to key change, making unauthorized decryption highly challenging. Next, resilient under pressure. This noise introduction ultimately lower image quality. The proposed algorithm demonstrates remarkable resilience even under significant noise level. The decryption image remains recognizable, ensuring the core information remains protected. In a sense, this study introduced a promising encryption technique that blends the complementary strength of DNA and encoded maps, resulting in powerful protection against unauthorized image access. By further exploring real-world application and comparison with existing methods, this approach holds potential for safeguarding sensitive visual data across diverse fields. This alternative combine highlights the synergy between DNA and coding maps, emphasizing the multi-layer security and resilience aspect.